In a land where sand dominates the horizon and water is almost non-existent, where over 95% of the territory is desert and rainfall is little more than a rare event, Saudi Arabia was forced to challenge the limits of engineering itself. Faced with one of the harshest climates on Earth, the country accomplished what once seemed impossible: the creation of a colossal steel water transport system capable of sustaining an entire nation by drawing water directly from the Red Sea. Every single day, billions of liters of seawater are captured by massive desalination complexes and pushed deep inland through an invisible river of Steelin, the immense network of pipelines stretching thousands of kilometers across scorching desert terrain. Transporting seawater across such vast distances is already an extraordinary engineering achievement, but transforming that salty water into fresh, drinkable water, suitable for human consumption, agriculture, and industry, is what truly earns Saudi Arabia global recognition. So how exactly is this hidden river of steel built, and how does it operate under such extreme conditions? But before we answer that question, don't forget to like and subscribe to our channel. Saudi Arabia has a population of over 37 million people, and nearly the entire nation follows Islam. One striking characteristic of the country is how its population is heavily concentrated along the coasts of the Red Sea and the Persian Gulf, while the vast interior remains an almost uninhabited expanse of desert. Saudi Arabia possesses what much of the world desires most: oil. But nature never gives everything at once. With more than 40 trillion liters of oil beneath its soil, the country still spends billions of dollars to produce every single drop of fresh water. Average annual rainfall is less than 4 inches, while summer temperatures frequently soar above 113 degrees Fahrenheit. To survive under these extreme conditions, Saudi Arabia built a nationwide water pipeline system. This network relies on high-strength carbon steel pipes, similar to those used in the oil and gas industry. Construction costs average around $3 million per kilometer of pipeline, not including auxiliary pumping stations and advanced desalination plants, each of which can cost tens of millions of dollars. But where does the water that feeds this massive system come from? The answer lies in an almost inexhaustible source: seawater. However, seawater contains approximately 3.5% salt, making it unsuitable for drinking or irrigation. That is precisely why desalination technology became essential, granting Saudi Arabia a virtually unlimited supply of usable water. The system transports water from enormous desalination plants located along the Red Sea. Every day, a single plant can convert roughly 7 million liters of seawater into drinking water, consuming vast amounts of energy in the process. The first step in building this nationwide water pipeline begins with manufacturing the pipes themselves. The pipes are typically made from high-strength carbon steel, similar to that used in oil and gas pipelines. To withstand constant pumping pressure, mechanical impacts during underground installation, and the extreme thermal cycles of the desert, rectangular steel plates are cut to pre-calculated dimensions, sufficient to be rolled into circular pipes with a diameter of about 6 feet and a wall thickness close to 1 inch. These plates then pass through multi-axis forming machines, where rollers gradually bend the steel until the edges meet, forming a raw pipe ready for the next stage of longitudinal welding. After welding is completed, the pipe passes through a water flow cooling line to reduce the temperature of the welded seam. The steel pipes are then carefully ground along all edges and corners to remove burrs and ensure geometric precision before further welding. The ends of each pipe receive welded bevels, creating ideal contact surfaces for connections between segments. Each pipe section typically measures about 40 feet in length, enough to reduce the total number of welds without compromising transport practicality. This design allows the pipes to be joined quickly, maintain pressure-tight seals, and remain structurally stable over the long term when installed along extensive land routes. Once completed, the steel pipes are taken to outdoor storage yards, where they are stacked in batches and properly identified for logistics and tracking. From there, they are loaded onto specialized transport vehicles with the assistance of forklifts or cranes and securely fastened to prevent deformation during transit. Finally, the sections are transported hundreds of miles to the construction site, where they are welded directly along the pipeline route. The installation process begins at large support areas distributed along the route. At these locations, the fully fabricated pipes are organized by diameter, length, and installation sequence. Engineering teams perform final visual inspections, checking alignment, coating condition, and identification markings. Proper organization in these areas is essential to maintain a continuous workflow, reduce delays, and minimize errors when operating under harsh desert conditions. At the same time, surveying teams define the exact pipeline route through the desert, using GPS systems, total stations, and terrain data. The alignment is marked directly on the ground with stakes and visible paint. This step ensures that the pipeline follows the most stable and efficient path, avoiding weak soils, shifting sands, and erosion-prone areas. For pipelines extending hundreds of miles, precise routing is critical to long-term structural integrity. Before excavation begins, The site must be cleared and leveled to allow the safe operation of heavy machinery. Temporary access roads are opened parallel to the pipeline to accommodate trucks, excavators, welding equipment, and material transport vehicles. In the desert environment, site preparation also includes dust control measures and sand stabilization to ensure visibility and worker safety. This is an essential stage to guarantee the smooth progress of the entire construction process. Once the route is defined, large excavators begin opening the trench along the marked alignment. The trench is excavated to precise width and depth, providing sufficient space for pipe placement and subsequent backfilling. The excavated soil is sorted on site. Suitable material is reserved for backfill, while unsuitable soil is discarded. Maintaining consistent depth and alignment is essential to prevent deformation or misalignment after installation. In certain sections crossing steep, rocky terrain, explosives are used to open trenches directly in solid rock, with controlled charges detonated in sequence to fracture the rock mass according to the planned route. The resulting trench has sufficient depth and width to safely accommodate the pipeline, even where mechanical excavation is impossible. This method allows construction to advance through extreme landscapes while keeping the pipeline buried, protected, and structurally stable. After excavation, the pipe is not placed directly on the trench bottom. A layer of selected material, usually fine sand or screened soil, is evenly distributed to form the bedding layer. This layer distributes loads uniformly and reduces stress concentrations on the pipe. The bedding is leveled and lightly compacted to reach the desired grade. In loose, dry desert soils, this step is crucial for long-term stability. For the construction of large-diameter pipeline routes, a construction corridor, approximately 130 feet wide, is prepared in advance, allowing the entire installation process to advance continuously at an average rate of about 1 mile per day. Pipe sections about 60 feet long are selected to reduce the number of field welds, which imposes very high demands on lifting, transport, and precise alignment during construction. At the welding site, an internal hydraulic alignment clamp is positioned inside the joint and expanded with 360-degree fixing shoes, keeping the two pipes perfectly concentric and aligned before and during welding. An automated welding operation, supported by a team of approximately 80 professionals and dozens of specialized machines, is capable of performing up to 150 welds per day on 42-inch diameter pipes, about 3.5 feet. After welding, each joint undergoes automated ultrasonic inspection to ensure the absence of internal defects. The coating team then performs abrasive blasting to clean the surface and applies a multi-component liquid epoxy coating, forming a durable, fully sealed protective layer before the pipes are lowered into the trench and backfilled. The assembled pipes are positioned into the trench with the assistance of side boom tractors, tracked vehicles designed specifically for large-diameter pipeline construction. Multiple machines operate in sequence along the route, each lifting a section of the pipeline with padded slings and steel cables to protect the coating. The assembly is lifted evenly and kept suspended as the machines move slowly along the trench. Precise coordination among operators is essential to avoid twisting, bending, or contact with trench walls. When alignment is correct, the pipe is gradually lowered, inch by inch, until it rests at the center of the trench on the prepared bedding. Throughout the process, surveyors continuously monitor elevation, alignment, and the natural curvature of the pipe to ensure there are no residual stresses. This method allows for fast, controlled, and highly precise installation, making it ideal for long, straight stretches across flat desert terrain. After placement, the trench is backfilled in multiple layers. The initial layer consists of fine material to protect the pipe coating, followed by the previously excavated soil. Each layer is mechanically compacted to achieve the required density, minimizing future settlement. In desert conditions, where soil structure can be affected by wind and extreme temperature variations, proper compaction is fundamental to pipeline durability. The process begins with direct seawater intake from the open ocean, conveying it inland and establishing a continuous, stable supply of raw water to the desalination plant. Large intake lines are initially positioned offshore, where teams carefully align each segment before lowering it with the aid of high-capacity cranes operating from barges or coastal platforms. As the pipeline advances toward the coast, individual segments are connected sequentially, forming a continuous conduit designed to operate under constant hydraulic load. Precise alignment is essential at this stage, as even small deviations can affect performance and flow efficiency over time. Once assembly is complete, the intake line is reinforced with support structures and securely anchored to the seabed. The desalination process begins when seawater is drawn through the pipelines directly into open intake screens. Intake occurs several hundred yards offshore, where barriers and filters prevent large floating debris and marine life from entering. A pipe with a diameter of about 25 inches can capture up to 15 million liters per day, equivalent to more than 10,000 liters per minute. At the intake point, Powerful pumps push the seawater toward the plant. During suction, some unwanted visitors may appear, such as jellyfish, crabs, and occasionally small fish. To prevent these organisms from entering the system, a large screen is installed to block any object with a diameter greater than about 0.18 inches. The water then passes through finer screens to remove remaining larger particles. Even after removing larger organisms, the water still contains many suspended sediments. The solution is a process called filtration, which takes place in tanks like these. In them, water flows downward through layers of sand using gravity alone. The spaces between sand grains are so small that only water can pass through, while suspended particles are trapped. The sand continuously moves downward, opposite to the water flow, and impurities adhere to its surface. After this stage, the water appears cleaner, but still contains countless microscopic particles. Everything larger than roughly 1/10 the thickness of a human hair is removed. Next, large mechanical paddles agitate the water, and the plant adds two chemicals: sodium hypochlorite, a disinfectant, and ferric chloride, a coagulant. The coagulant causes fine particles and residues to clump into larger flocks, which then settle at the bottom of the tank. Most of the dirt has now been removed, but the water is still far from clean enough for the desalination stage. After fine filtration, the water enters the cartridge filtration system, the last line of defense before reverse osmosis. Inside each housing are several cartridges made of layers of highly compacted fibers, with pores ranging from 1 to 5 microns. As water flows from the outside to the center of each cartridge, microscopic particles become trapped between the fibers, while clean water passes through the cartridge wall and continues onward. When a cartridge becomes saturated, engineers remove and replace it to ensure the system always operates at maximum efficiency. The seawater then proceeds to the most critical stage: separating salt from water. Salt is extremely difficult to remove because salt ions bind strongly to water molecules through electrostatic attraction. To break this bond, the system must apply extremely high pressure. The water then enters the process known as reverse osmosis, where the real magic happens. The concept is simple: apply pressure greater than the natural osmotic pressure, forcing water through an ultra-thin reverse osmosis membrane, while salt and other impurities are retained. To generate this pressure, the plant uses high-power centrifugal pumps. Each component of the pumping system controls a specific pressure stage, which increases gradually as the water passes through successive compression phases. At the exit of the final pump stage, pressure reaches about 870 psi, roughly 60 times atmospheric pressure, enough to separate water from salt at the molecular level. After the first reverse osmosis stage, the water is already nearly salt-free, but it still contains traces of ions and microminerals that must be completely removed to meet certain drinking water standards. For this reason, the water undergoes a second reverse osmosis stage, where even finer membranes operate under lower pressure but with greater salt removal efficiency. This stage reduces the electrical conductivity of the water to extremely low levels, eliminating remaining ions and bringing the water to an almost total level of purity. The final result is a flow of ultra-clean water, nearly perfect in purity, ready for remineralization or distribution. After passing through the reverse osmosis membranes, the water is already suitable for irrigation, but its pH still needs adjustment before human consumption. To do this, the plant corrects the pH, usually by adding a small amount of acid or neutralizing solution to bring the water back into a safe range. Reverse osmosis desalinated water also contains much lower amounts of essential minerals compared to regular drinking water. So to improve taste and overall quality, small amounts of minerals such as calcium and magnesium are added during the remineralization process. This stage restores the water's mineral profile, adjusts pH, increases alkalinity, and brings back a natural taste, creating water that is not only safe but also healthier and more pleasant to drink. Once desalinated, the water is distributed to residential areas through a modern pipeline network to serve the population of Saudi Arabia. However, the cost is extremely high, around $5 per cubic meter of water, something that in the United States may cost only a few dozen cents. Now you know this entire impressive process. See you in the next videos.